Quantum Physics and the Problem of Consciousness. Unit 1, Classical Assumptions, Quantum Differences. Section 1, The Assumptions of Classical Physics. I'm going to be using three writers in particular to present the view that consciousness is ultimately grounded in quantum physics. They are the Australian science writer David Hodgson, the American physicist Henry Stapp, and the French physicist Bernard d'Espagne. They all reject the determinist, reductive, and physicalist scientific consensus as to what consciousness might be. This conventional view is based entirely on classical physics and completely ignores quantum theory. As Hodgson comments, those who take this position regard themselves as having a tough-minded empirical approach which eliminates mysterious entities such as witches, ghosts, and spirits. Quote, contrary views are said to be unscientific and tender-minded, end quote. Daniel Dennett can be taken as a prominent and characteristic representative of this conventional position. The three theorists above reject this consensus precisely because it rejects quantum theory. They instead urge direct confrontation with the bizarre quantum concepts, especially those which flatly contradict the assumptions of classical physics. For example, the fact that quantum mechanics espouses indeterminism rather than determinism, holism rather than reductionism, and that in some versions it posits the notion of some mysterious reality underlying everyday appearances. Plus, of course, and most importantly for our purposes, the fact that quantum mechanics promotes the idea that consciousness may play an important role in physical processes. So, in this unit, we'll look at the fundamental differences between classical and quantum physics. The earlier classical physics had emerged from the study of the observed motions of the planets and large terrestrial objects. Perhaps as a consequence, it espoused the conception of the entire physical universe as composed of miniaturized versions of these large visible objects, as Henry Stapp observes. The most prominent exponent of this view was the great physicist Isaac Newton. In 1704, he described these apparent building blocks of physical reality as, quote, solid, massy, hard, impenetrable, movable particles. In other words, much like billiard balls, and these tiny billiard balls were conceived as acting upon each other almost exclusively via direct physical contact, apart from gravity. Classical physics also made a number of basic assumptions as to how this billiard ball universe was governed. Broadly, these assumptions concern two areas of metaphysics. Firstly, the mode of existence of physical objects, and secondly, the nature and effect of observations or measurements carried out on these objects. The physicists Amit Goswami and Hodgson have both attempted to identify and analyze these assumptions, especially in relation to how they have been challenged by the assumptions of the new physics. While considering these, however, it must be borne in mind that all these statements from classical physics are simply metaphysical assumptions. None of them are or could be empirically tested. They are not products of applying the scientific method, but rather assumptions designed to guide its application. According to B. Alan Wallace, in addition to being rooted in Newtonian mechanics, many of the assumptions of classical physics also originate from monotheistic creator-God theology. For example, the notion that matter is passive and or dead, and only reacts when acted on by external forces. In listing the assumptions of classical physics, Goswami points first to strong objectivism. Objects are out there. In philosophical terms, this could be described as naive realism. Specifically, mind and consciousness play no role in creating the external world. Hodgson notes that in the classical world, all physical objects exist continuously over time, though can change to some extent. Objects exist independently of being observed or interacted with. At any particular time, objects have definite dimensions and mass, and a definite mechanical state, including location and motion, both velocity and rotation. Motion is continuous over time and infinitely divisible. All particles have a definite position in space and definite motion. All as would be consistent with common sense. But, of course, all of these assumptions of classical physics have been challenged by the new physics. For example, the notions of definite dimensions and mass are challenged by relativity theory, and all the other classical assumptions are flatly contradicted by quantum theory. Physicists have concluded that, at least at the microscale of atoms and subatomic particles, classical assumptions have to be abandoned. Classical physics also promoted the principle of locality. This rules out any possibility of simultaneous causal action at a distance. This is contradicted in quantum theory by, for example, entanglement. This is a physical phenomena that occurs when pairs or groups of particles are generated or interact in ways such that the quantum state of each particle cannot be described independently. Instead, a quantum state must be described for the system as a whole. The principle of locality is also violated by quantum tunneling. In this phenomena, a low-energy particle can tunnel through a barrier which in the classical world would be impenetrable, and without requiring any time to make this transition. As Hodgson says, quote, "We know now that spatially separated events can be correlated instantaneously or non-locally at the quantum level, so that if different aspects of, say, a visual experience are indeed present non-sequentially to consciousness, it seems reasonable to invoke quantum non-locality to explain this." End quote. He also insists that non-locality is, quote, "a very strong indication of the close relationship between mental events and the development of quantum physical states, end quote. As to observation or measurement, in the classical world, there were no theoretical limits on accuracy. It was, of course, accepted that absolute accuracy might not be attainable in practice. However, classical physics recognized no theoretical limits on the smallness of any possible disturbance from observation or measurement, or on the accuracy with which such disturbance could be measured. Imprecision in observation and measurement did not mean that an object's actual position and or motion is in itself uncertain or imprecise. Following the advent of quantum mechanics, however, observation and measurement became A, subject to theoretical uncertainty, and B, dependent on the consciousness of the observer. An early statement of this came from London and Bauer in 1939, quote, "It is only the consciousness of an I who can separate himself from the system, and by virtue of his observation set up a new objectivity," end quote. Hodgson comments, quote, "If measurement is effected by the first registration on human consciousness, then it is not surprising that the mathematics of quantum physics, dealing with the objective world, does not represent it. Further, a reasonably clear distinction is drawn between measurement on the one hand and the physical processes which are represented by the mathematics of quantum physics on the other," end quote. This philosophy of quantum physics is amplified by Henry Stapp, quote, "The proper subject matter of science is not what may or may not be out there, unobserved and unknown to human beings. It is rather what we human beings can know and can do in order to know more. Thus, they formulated their new theory called quantum mechanics or quantum theory around the knowledge acquiring actions of human beings and the knowledge we acquire by performing these actions, rather than around a conjectured, causally sufficient mechanical world. The focus of the theory was shifted from one that basically ignored our knowledge to one that is about our knowledge and about the effects of the actions that we take to acquire more knowledge upon what we are able to know," end quote.